Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad Wa campus. These slides have been edited from these two sources given here. The topics of this lecture are instruction set of Intel family of microprocessors. In particular, our discussion is focused on the instruction set of 8086 microprocessor with some examples from other members of the family. And arithmetic instructions, add with carry, subtraction, and subtraction with borrow will also be discussed in this lecture. Microprocessors, in particular 8086 microprocessor, supports 6 types of instructions. Briefly about instruction set, actually for every microprocessor there is a set of instructions that can be used to write programs for that microprocessor. Every instruction is executed by the microprocessor to perform a simple task, and then the setup instructions that forms a program altogether executes or solves a big problem that is normally called the application. In Intel family of microprocessors, there are normally 6 types of instructions. The first is data transfer instructions. These instructions are responsible to transfer data from memory or register to memory or registers, or also it can transfer data from the and to the input and output ports. Then there are arithmetic instructions that are responsible to perform arithmetic operations like addition and subtraction. And the third group is logical instructions that include instructions to perform logical operations like AND, OR, exclusive OR, and etc. There are some string manipulation instructions that operates on string data only. For example, MOVS, which is a variation of the data transfer instruction move. But MOVS is responsible to transfer or to move string data from one location to the other. Then there are processor control instructions. Processor control instructions controls the operation of the processor, and also these instructions are responsible to change the status of the microprocessor. For example, to set the carry flag, to clear the carry flag, there is an instruction STC. To set the carry, for example, and to set or clear the direction flag, and there are many other similar instructions. And finally, there are control transfer instructions. These instructions are responsible to transfer the control flow from one location inside the program to another. For example, jump and call instructions are in this category of instructions. Memory address calculations is needed to access a particular place or byte in the memory. In the microprocessor, there are 2 units. One is the bus interface unit and the other is execution unit. There are some registers in the bus interface unit, for example, instruction pointer and segment registers. And there are other set of registers inside the microprocessor in the execution unit. Bus interface, these registers in the bus interface unit, and particular bus interface unit in itself, is responsible to compute addresses and to fetch data and instructions from the memory, while the execution unit is responsible to execute an instruction to store, and these registers are used to store the operands and the result after computation. To access memory location, microprocessor first needs to calculate or to compute memory address, which is also called the physical address. And the physical address calculation begins with the segment register. So whatever the segment register is being accessed, the corresponding whatever the segment of the memory is being accessed, the corresponding segment register here would provide a 16-bit segment number, and that segment number is then left shifted by one hexadecimal digit, or that is also equivalent to left shifting by 4 binary digit, or that is also equivalent to appending 4 zeros in the binary or one hexadecimal 0 at the right side to create a 20-bit value. So this 16-bit segment register left shifted by one hexadecimal digit would make it a 20-bit address, and this 20-bit address is then the starting address of that particular segment. If the segment register is a code segment, then this address would be the starting address of the code segment in the memory, and if it is the data segment, then this 20-bit address would be the starting address of the data segment memory. After creating the starting address of the segment, an offset value, which is normally a 16-bit value in the 8086 microprocessor, this offset value is the address, a relative address from the starting address of the segment. For example, if this value is 20, then this address would locate or address the 20th byte of that segment. So this offset value is normally added with the starting address of the segment, which is here, using an adder, and after addition a 20-bit address is calculated, and that 20-bit address is the memory address of that particular byte or location inside the corresponding segment. So in coming slides, whenever we are talking about memory accesses, then the memory address is calculated this way. A segment is accessed, and that number in the segment is left shifted by one hexadecimal digit, and then a 16-bit offset value computed through different ways defined by the addressing modes, and then finally a 20-bit physical address is computed. In arithmetic instructions, there are a number of instructions including add with carries, subtraction with borrow, and so on and so forth. In addition, in add instruction, add instruction performs the arithmetic operation addition, and this is one form of group of variations or group of forms of the add instruction, where ADD is the opcode of the add instruction, and ADD means addition. Then there is a space, and then there is the first argument of this instruction, which can be a register, and it can also be a memory, followed by a comma, and then there is another second argument of this instruction, which can also be a register, and it can also be a memory location. Remember that both of the arguments cannot be, or both of the operands cannot be memory at the same time. This is similar to the move instruction, where both of the operands cannot be memory, except the move s instruction, which is string manipulation instruction, where both of the operands can also be memory. So that allows memory to memory transfer. But here in the add instruction, memory to memory addition is not allowed. In this format, the first form is ADD, and the first operand is a register, the second operand is a register. And in this case, this instruction would add the content in the register 2 with the content in register 1, and will store the result in register 2. So this is equivalent to register 2 is equal to register 1 plus register 2. So whatever is the value in the register 1, that is added with the content of register 2, and the result is stored back into the register 2. So here register 1 and register 2 are the sources of data, and register 2 is the destination of the data as well. In this form, here is an example. For example, add AX and BX. So this instruction add would add the 16-bit content of AX register with the 16-bit content of BX register, and would store the result in the AX register. So this is equivalent to AX is equal to AX plus BX. Then there is another form of add instruction, and that is when the destination of the result is a register and the source of the data is a memory location. So this instruction would add the content of this memory location with the content of register 2 and would store the result back into register 2. Here is an example where add instruction would add the 16-bit content stored in the X register with the 16-bit content of memory location and the data segment addressed by this offset value, and would store the result back into the X register. So here this is the addressing mode, direct addressing mode, where the memory address is provided directly as part of the instruction. So 1234H is a 16-bit offset value that is provided directly, and this offset value is added with the data segment content, which would give us a 20-bit physical address, and then 2 bytes. One at this address calculated, and the other byte is the at the next higher address. So the 2 bytes are then added with the 2 bytes in the X register, and the result is stored in the X register back again. Okay, and the third form of add instruction in this category is when the destination of the operand or the result is the memory location and the source is the register. The source is a register. This instruction would add the content of register 1 with the content at this memory location, and the result is stored back into this memory location. For example, one more thing about this instruction, that here the address is directly provided, the offset address is directly provided as part of the instruction, so this is called direct addressing mode. And when that address is provided through the register, then this becomes indirect addressing mode. And similarly, there can be other addressing modes can also be included and can also be used, and just like the addressing modes we used in the case of move instruction. And in this category, here we have an X register, and then there is a BX register enclosed in brackets. So this form is a register indirect addressing mode, where the offset address of the memory location inside the data segment is provided through the BX register. So this instruction would add a 16-bit value in the X register with a 16-bit value in the data segment memory location addressed by the offset address stored in the BX register, and the result is stored at the same memory location. And similarly, add instruction can also operate on immediate data with the two forms, where the destination of the result can be a register and it can also be a memory location. So in case of register, as the memory as the destination of the result, the data, the immediate data is added with the content of the register, and the result of addition is stored in the same register here. So data plus register is the result is stored in this register, which is given here. An example of this form of instruction is here: add AX comma 1234H. So 1234H is the immediate data, and this 16-bit immediate data is added with the X register, and the result is stored back into the X register. Remember that it is also possible that the value here and the 16-bit value stored here, when they are added, the result may be larger than 16-bit. In that case, the carry generated at the final, at the most significant bit position, is stored in the carry flag in the E flags or the flags register. This value 1234H is an immediate value, and it is not an address. If it would be enclosed in the bracket, then this would become a memory location. So the data, 16-bit data at that memory location would be added with the X, and the result would be stored in the X register. So this example is here, where the memory is the destination, and the immediate data is provided as part of the instruction. So the data plus the immediate data provided as part of the instruction is added with the content of this memory location, and the result is stored at the same memory location. Here is an example where this 432H in hexadecimal is a 16-bit value. This 16-bit value is added with the 16-bit content in the data segment memory location addressed by this offset address, and the result is stored back into the same memory location. And finally, in this form, there is an accumulator register used as the destination of data. The accumulator can be used as an 8-bit, or it can also be used as a 16-bit register. So the 8-bit immediate data is added with the L register, and the result is stored back into the L register. For example, 8 L comma 1 to H. So this 1 to H is an 8-bit value, and this 8-bit immediate value is added with the 8-bit content of the L register, which is the accumulator, but it is the low byte of the accumulator, so the low part of the accumulator. So this 8-bit content is added with 1 to H, and the result is stored back into the L register. A 16-bit version can also be included, where a 16-bit immediate value is added with the 16-bit content of the X register, and the result is stored back into the X. Here is the example where the 16-bit value in 1234H is added with the 16-bit content of the X register, and the result is stored back into the X register. There are many other examples and addressing modes plus larger registers are also included in these examples. So it means they are not only for the 8086 microprocessor, but they are also for other later members of the Intel family of microprocessors. Here are some assembly language instruction, and here is the explanation of the operation that instruction perform. For example, add ALBL, it is using the addressing register addressing mode, so L plus BL is stored in the L. It is a 16-bit mode where the 16-bit content in the DI is added with 16-bit content of the CX register, and the result is stored back into the CX. Add EBPEX, so obviously these registers are not available in the 8086 microprocessor, so they are available in the later microprocessor, higher microprocessors. So the 16-bit content, 32-bit content are added, and the result is stored back into the 32-bit register. Here an immediate value, 8-bit immediate value is added with the 8-bit CL register, and the result is stored back into the CL. Here the 16-bit immediate value is added with BX, and the result is stored in the BX register. And again the immediate value, 32-bit immediate value is added. Here the addressing mode, memory addressing mode is annulled, where the content 8-bit content of the L register is added with the data 8-bit data in the data segment memory location addressed by this offset address in the BX register. And similarly here the data segment, the stack segment, 1 byte content from the stack segment is the register is base pointer, so the default segment with base pointer register is the stack segment. So byte content of the stack segment addressed by the offset address in the P register is added with the 8-bit content in the CL, and the result is stored into the CL. And here an 8-bit content is added from this memory location and is added with the 8-bit content in the L register, and the result is stored back into the L. And remember that this instruction represents that this is not an 8086 microprocessor, but this instruction can be executed on higher members of the family. For example, 8386 and 80486 or Pentium computers. And here the addressing mode is different. It is the word content or the 16-bit content at this memory location in the data segment addressed by the offset address calculated as the 16-bit content in the SI plus 2. So that would give us an offset address, and the 16-bit content at this offset address in the data segment memory location is added with the 16-bit content in the BX register, and the result is stored into the BX register. And similarly, here temp is a variable that provides the offset address, and the segment is data segment. So the 8-bit content in the data segment memory location addressed by the offset address provided or stored in this temp variable is added with the 8-bit content in the CL, and the result is stored into the CL register. And here this is here the 16-bit content from the data segment memory location addressed by the offset address computed as temp, the offset value stored in temp plus the offset 16-bit offset value stored in the DR register. Both of these values are added and a 16-bit offset address is calculated. And the 16-bit data or word size data from this memory location is added with the content in the BX register, and the result is stored back into the BX register. And here two registers are used, base register plus index register, which is destination index here, and I is missing here, so this is a destination index. So the 8-bit content in the DL register is added with the data segment, the 8-bit content in the data segment memory location addressed by BX plus DI, and the result is stored back into the same memory location. And here an immediate data is used, but a memory location is used here, so it is not clear what is the size of the addition. So a byte pointer directive is used. So this instruction would add this 3 as an 8-bit value with the 8-bit value in the data segment memory location addressed by this offset address, and the result is stored back into the same location. This is an addressing mode which is called scaled addressing mode, which is not available in the 8086 microprocessor, but available in higher members of the family. So here the data segment memory location addressed by the offset address computed as follows. The 32-bit content in the EX register is added with the 2 times the 32-bit value in the E6 register, and this would give us a 32-bit offset address, and this offset address would locate a 16-bit value in the data segment memory location, and that 16-bit value is added with 16-bit content in the BX register, and the result is stored here in the BX register. And here we can see RX and RBX, which are 64-bit registers, and these 64-bit values in these registers are added. And so these two examples are the 64-bit addition examples. Here the same pattern is used as was used here, where the offset address is provided or are computed by adding the 64-bit value in the RX register and 64-bit value in the RCX, and this would give us a 64-bit offset address, and this 64-bit offset address is added is added with the starting segment address of the segment to compute the physical address. And so a 32-bit value or double word this memory location in the data segment is added with 32-bit value in the EDX, and the result is stored back into the EDX register. So there are a number of other variations, and add instruction can be used in different addressing modes and with different register sizes depending on the microprocessor. Add with carry, it's a slightly different version of the add instruction, but the addressing modes are quite similar. But here add with carry instruction not only adds 2 operands defined by the 2 operands here, defined by the 2 arguments here, but in addition it also adds the content of the carry flag. So just like the add instruction, this is the general format of the add with carry instruction, and in this category we can have add with carry where both of the arguments or both of the operands are registers, where the content of register 1 and register 2 are added, and the content of the carry flag is also added, and the result is stored back into the register 2. An example of this is add with carry xbx, where x plus bx plus the content of the carry flag, and the result is added with the the result is stored in the X register. So while this addition is performed, the content or the value of the carry flag at this moment is important. So if the carry flag is 0, then a 0 is added with X plus Bx, and if the content of the carry flag is 1, then a 1 is added with the X plus Bx, and the result is stored in AX register. Similarly, in the other addressing form, in this category, the source of the addition is a memory location, and the destination is a register. So the content of the carry flag plus the memory location, the content at this memory location is added with the content of register 2, and the result is stored into the register 2. For example, here add with carry. So a 16-bit value in this data segment memory location addressed by this address is added with X, plus the carry flag is also added, and the result is stored into the AX register. And the memory can be the source of the result, where the carry flag plus the content of a register and the content of a memory location are all together added, and the result is stored back into the same memory location. For example, the 16-bit value in the X register plus the carry flag value is added with 16-bit value in this memory location, and the result is stored back into this memory location. And similarly, add with carry can also be used with immediate data, and the destination of the addition can be a register, and it can also be a memory location. In case of the destination of the result is a register, the carry flag plus the immediate data plus the value in the register are added, and the result is stored in the destination register here. This is an example where the 16-bit immediate value 1234H is added with 16-bit content of the AX, plus the value of the carry flag is also added, and the result is stored back into the AX register. In case the destination of the result is a memory, the content of the carry flag plus the data plus memory is added, and the result is stored in the memory location. Here is an example where 432H is immediate value. This 16-bit immediate value is added with the 16-bit value in the data segment memory location addressed by this offset address, and a carry is also added, and then the result is stored back into this memory location. Add with carry here, this D is redundant, so this is a typo, so this is the same ADC instruction. So this D is and should not be there. So accumulator immediate data can also be added with the accumulator, and the 8-bit immediate data can be used, and 16-bit data can be used. So in case of 8-bit immediate data, the low part of the accumulator register L is used, and in case of 16-bit data, accumulator can be used. So this is an example of 8-bit immediate addition with carry. So this 8-bit 12H value plus the carry flag plus the 8-bit content in L register are added, and the result is stored back into the L register. And the same can happen for the 16-bit value, and the same can happen for even higher registers available if they are available. Then we subtraction. Subtraction, just like addition, can have different forms. This is the template or the structure of subtraction instruction, where SUB means subtraction, that is the opcode of this instruction, and this subtracts this value provided as the memory or provided as the register from this memory location or this register, and the result of the subtraction is stored back into this operand. This is the source of data, and this is the source as well as destination of computation. So in this category, we have three forms: a sub, register 2, register 1, where both of the operands are registers. So the content in register 1 is subtracted from the content in register 2, and the result is stored in register 2. For example, SUB AX BX, where the 16-bit value in the BX register is subtracted from the 16-bit value in the AX register, and the result is stored in the AX register. One of the argument or one of the operand can be a memory location, where the source of the data is the memory location, while the destination of the result is a register. So the content in the memory location is subtracted from the content in register, and the result is stored into the register. As an example of this form of instruction, subtraction instruction is SUB AX, 1, 2, 3, 4H enclosed in the bracket. So remember that when a value is enclosed in the bracket, then that is not a value, but it represents an address. So this is a memory addressing mode. This is direct memory addressing mode, where the offset address is directly provided as part of the instruction. So a 16-bit value in the data segment memory location addressed by this offset address is subtracted from the 16-bit value in the AX register, and the result is stored back into the AX register. Similarly, the destination of the result can be a memory location, where the content in this register is subtracted from the content from this memory location, and the result is stored back into the memory location. For example, here the 16-bit content in the AX register is subtracted from the 16-bit content in the data segment value addressed by this offset address, and the result is stored back into the same location. Subtraction instruction is also available, where the immediate data is provided, while the destination of the result can be a memory location, and it can also be a register. One more thing about this form is that both the source and destination cannot be a memory location. This is not allowed. For example, if you use SUB memory 1 and memory 2, so this is not allowed. Memory to memory access, or memory to memory subtraction, or memory to memory addition, or memory to memory data transfer is not allowed by these instructions. Okay, so here the immediate value here is subtracted from the register, and the result is stored back into the register. For example, this 1, 2, 3, 4H is an immediate 16-bit value. This 16-bit value is subtracted from the 16-bit content in the AX register, and the result is stored back into the AX register. Similarly, the source can be immediate, while the memory can be as the destination operand. So the data in the provided here is subtracted from the data in this memory location, and the result can be stored in the same memory location. For example, 432H is a 16-bit value, and this 16-bit value is subtracted from the 16-bit content in the data segment memory location addressed by this offset address, and the result is stored back into the same memory location. And subtraction is available just like addition, with immediate data and accumulator, and these addressing modes are not that much different from this addressing mode with subtraction, where this 8-bit data in this form, the 8-bit data is subtracted from the content of accumulator, and the result is stored back into the accumulator. And this is an example where 1 to H is an 8-bit content, and this 8-bit content is subtracted from the 8-bit content of the accumulator, and the result is stored back into the accumulator. 16-bit version or form of this form of subtraction is also available, where this 16-bit value is subtracted from the 16-bit content of the accumulator AX register, and the result is stored back into the AX register. Just like addition, where 8 with carry is available, there is a subtraction with borrow as well, which not only subtract one value from the other but also subtract the content of the carry flag from the result. So three forms are available. In the first category, where there are two operands and both of the operands can be a register or it can also be a memory. And remember that even in this instruction, subtraction with borrow, both of the operand cannot be memory at the same time. When both of the operands are registers, then the content of register 1 and the content of the carry flag are subtracted from the content of register 2, and the result is stored back into the register 2. So here is an example where SBB x bx means x minus bx is first computed, and then the content of the carry flag is subtracted from the result computed here, and then the final result is stored in the x register. So not only bx is subtracted from x, but also the content of the carry flag is also subtracted from x, and the result after these two subtraction is then stored in the x register. So subtraction with borrow subtracts one value from the other, as well as subtracts the carry flag value from the result. This subtraction with borrow instruction is also available when the source of the value is the memory location while the destination is the register. So in this case, the content in the memory location and the content of the carry flag are subtracted from the content in this register 2, and the result is stored in the register 2. For example, SBB x, 1, 2, 3, 4, 8. So here a 16-bit value in the data segment memory location addressed by this offset address and the carry flag both are subtracted from the X register, and the result is stored back into the X register. Memory location can be the destination of the result, like here, where the content of register 1 and the content of the carry flag are subtracted from the content in the memory location, and the result is stored in this the same memory location. For example, SBB 1234H, X, the 16-bit value in this X register is subtracted from the 16-bit value in the data segment memory location addressed by this offset address, and then the carry flag value is also subtracted from the value in this memory location, and then the final result is stored at this memory location. And similarly, with SBB, immediate data forms are also available, where the immediate data is subtracted from the register, while in the other form, immediate data is subtracted from the value in the memory location. For both of these forms, these are the examples where the immediate value 1234H is the 16-bit immediate value is subtracted from the X register, and then the carry flag is also subtracted from the result, and then the final result is stored in the X register. While here the 16-bit immediate value and the carry flag are subtracted from the 16-bit value of the data segment memory location addressed by this offset address here, and then the final result is stored at this memory location. And just like the subtraction, subtraction with borrow is also available with only accumulator and immediate data. So in this example, the 8-bit immediate value and the carry flag are subtracted from the 8-bit content in the L register, and the result is stored in the L register. And similarly, the 16-bit value here, 1234H, is subtracted from the 16-bit content stored in the X register, and then the carry flag is also subtracted from the result, and then the final result is stored in the X register. So these subtraction with borrow and addition with carry, these instructions are useful instruction when a microprocessor has a smaller register, while the addition or the subtraction needed is larger than the registers. For example, in the 8086 microprocessor, there are 16-bit registers, and if we need to carry a 32-bit addition or 32-bit subtraction, then these instruction add with carry and add with borrow subtraction with borrow and add with carry instructions are useful. These are the instructions that were discussed in this lecture. Other instructions, arithmetic instructions, will be discussed in